Welcome to lecture 12th of module 3 of the course called Game Theory and Economics. Before we start this today's lecture, let me briefly recapitulate what we have been doing so far. What we have been doing is that we have been discussing the application of Nash equilibrium in auctions. The first kind of auctions that we have discussed so far is what is known as the English auction, also called the second price sale bid auction. So, that was what we have discussed before. We have seen that there are infinite number of Nash equilibria in second price sale bid auction. What we shall start discussing today is what is known as Dutch auction or so the difference of this auction with the second price sale bid auction is that in this auction the price that the winner gets of the auction is not the second highest price, but the first price. That is, the price that he is quoting is going to be the price that he is paying for the good. So, in why is it called the Dutch auction? What happens in or what used to happen in Holland in many cases is that price is to come down from above, and when it comes down from above auction prices, whenever the auctioneer finds at least one person who is ready to pay that price, that person gets the good and paying that price. So, here the second highest price does not matter for this auction, and the person who is ready to get the good is going to pay the price which is the highest price, not the second highest price, and that is why it is called the first price sale bid auction. So, in terms of our language, in terms of game theory, it can be represented as the following. And finally, preferences of the players. Here a difference will come compared to the second price auction. When a person gets the commodity, it is given by his valuation for the commodity minus BI if A or So, if I is getting the commodity, then he is getting a valuation of Vi, which is how he values the commodity, and from this we have to subtract the price that he is paying, which is Bi. It is not the second highest price, it is the price that he is quoting, and this will happen in two circumstances. One is if his bidding, that is Bi, is strictly greater than the highest bidding of other players, which is B bar, and if it can also happen, Vi minus Bi can also happen if person I's bidding is same as the bidding of other players, highest bidding of other players, but person I's index, that is I, is lower than those players who have submitted P bar, and 0 otherwise. So, if the bidding of this player is less than B bar of it, or it is equal to B bar, but index of other players are less than I, then person I does not get the commodity and he gets a payoff of 0. So, this is the setting. Now, let us look at what kind of Nash equilibrium that can be obtained from this setting. Let us look at the following biddings. This was a Nash equilibrium in the second price auction, but notice this cannot be a Nash equilibrium here, because what will happen is that in this case player 1 is getting the object by bidding V1, his valuation, and every other player is bidding his own valuation, but player 1 can still get the object if he reduces his bidding from V1 to V2, and in that case his payoff is going to go up. His payoff is going to go up to V1 minus V2, whereas presently he is getting V1 minus V1, which is 0. So, this is not a Nash equilibrium in this setting. What can be a Nash equilibrium? Let us take the following. This is a Nash equilibrium. What is happening is that player 1 and player 2 both are submitting bids which are equal to V1, and other bids are less than V1, because we know that V3, V4 etc. are less than V1. So, player 1 here is also getting the object and he is getting a payoff of 0. If he deviates, if player 1 deviates and bids something more, suppose he bids B1 which is greater than V1, then payoff is going to be V1 minus B1, which is less than 0, whereas presently he is getting 0. So, by deviating upwards, that is bidding something more, he is strictly worse off. If he bids something less, he will lose the object, he is not going to get the object, and so if he loses the object, his payoff becomes 0. So, he is not better off. Therefore, this is a Nash equilibrium. This is I have not specified the calculations of other players, but it will be a Nash equilibrium for the following reason, that right now other players are not getting any payoff, they are getting 0 payoff. Now, if they want to get the object, then they will have to outbid player 1, but if they outbid player 1, then the price that they will be quoting will be more than V1, which is more than their individual valuations. and if this is more than your individual valuation, then you are making a negative payoff, which means that by trying to get the object, they are going to get a negative payoff. Otherwise, if they do not get the object, their payoff remains 0, whatever they bid. So, from other players' point of view also, deviation is not profitable, and hence this is a Nash equilibrium. One interesting characteristic of this first price seal bid auction is that in the Nash equilibrium, player 1 will definitely get the object. Notice this was not the case in case of second price seal bid auction. There it could happen that other players are also getting the object, and the reason is the following, that player 1, if he does not get the object, it must be the case that someone else is getting the object. So, let us call that someone to be I. And if I is getting the object, then it must happen that B I is greater than B 1. Now, if B I is greater than B 1, then it can happen in two cases. B I is greater than equal to V 1, because I do not know exactly the value of B 1. So, there are two cases, one is B I is greater than equal to V 1, or B I is less than V 1. These are the only two possibilities. Now, if B I is greater than equal to V 1, then the player I who is getting the object is making a negative payoff, because his valuation is V I, which is less than V 1. So, he is getting the object, but his valuation is minus of B I minus V I, which is a negative quantity, and he can do better by setting B I is equal to V I, in which case he will get 0. So, this is not a Nash equilibrium. The other possibility is that B I is less than V 1. Now, can this be a Nash equilibrium? If B I is less than V 1, this is not a Nash equilibrium for the following reason. In this case, player 1 can always outbid player I, because his valuation V I is V I. So, he can always afford to bid something which is more than B I, but less than V 1. In fact, he can bid equal to B I and get the object, because the tie breaking rule is that player 1 gets the object if he ties with someone else. So, again, this cannot be a Nash equilibrium, because in this case B 1 will be equal to B I or more than B I, and which means that player 1 will get the object. So, player I cannot get the object in this case also. So, we are left with the possibility that in Nash equilibrium, player 1 always gets the object. There is another interesting property of Nash equilibrium in first price auction, which will be presented in terms of an exercise. Is the following. This is the exercise. In a Nash equilibrium of first price seal bid auction, show that the two highest bids are the same. One of these bids is submitted by player 1 and the highest bit is at least V2 and at most V1. Show also that any action profile satisfying these conditions is a Nash equilibrium. So, what we are required to show is the following. What is being said is that if you have Nash equilibrium, then this Nash equilibrium must satisfy some characteristics. Let us call these characteristics as A. And what are these characteristics? How is A described? A will be specifying an action profile where the bits are suppose B1, B2, Bn, where B1 is equal to Bi for I is equal to 2 or 3 or 4 etc., or n, and these two, that is B1 is greater than Bj for j 2 and j is not equal to I. So, this is what is being said, and another part of this A is that B1 is greater than equal to V2, but less than equal to V1. So, this is how A is described. A is describing some property of a particular kind of profiles. In these profiles, player 1 is making the highest bit and his bit is matching with the bit of another person, at least another one person, just one person. And we can in fact say that it can be possible that more than one person is bidding same as player 1. So, B1 is equal to Bi, where I can be 2 or 3 etc., or n, and bits of other players means player 1 and besides player 1 and player I, the bits of other players we call it Bj, those bits will be less than B1. And finally, we have this important characteristic that the highest bit, that B1, must be lying between two bounds. Its lower bound is given by V2 and the upper bound is given by V1. So, we have to show that if I have Nash equilibrium, then that Nash equilibrium must satisfy this characteristic A. Now, if I have to show that Nash equilibrium satisfies A, then I can show the same thing by showing that not A implies not Nash equilibrium. That is, if I do not have satisfaction of A, then I do not have Nash equilibrium. That will guarantee me that Nash equilibrium is implying A. This comes from the fundamental mathematical logic that suppose A is sufficient for B, then B is necessary for A. So, we have to show that if A is not satisfied, that some of these three characteristics are not satisfied, then we will not have Nash equilibrium. So, suppose this is not satisfied, that the bidding of player 1 is not equal to the highest bid of other players. If this is not satisfied, now if this is not satisfied, then obviously this is not Nash equilibrium. This is for the reason that in that case player 1 will lower his bid and bid equal to B1, because his payoff is given by V1 minus B1. As B1 declines, his payoff rises. So, he will always like to bid as little as possible. So, this is E1. Hence, if this is not satisfied, we do not have Nash equilibrium. Player 1 will have profitable deviation. What is the other characteristic that must be satisfied? That this highest payoff must be greater than the other bids. This is very easy, we have seen this before. We have proved this before. If some other player is bidding more than B1, then that player will get the object, and which we have just proved that cannot happen. In Nash equilibrium, player 1 must get the object. So, no further elaboration is required for this point. The third point is this. If this is not satisfied, then what happens? Which means that there are two possibilities. V1 is strictly less than V2, now if B1 is less than V2, then that cannot be a Nash equilibrium, because other players, for example player 2 will in that case outbid player 1 and get the object, and as long as his bid is less than V2, he will make a positive payoff, which he is not getting here, because I know that in Nash equilibrium, so far the Nash equilibrium that we have considered, player 1 is getting the object. So, player 2's payoff is 0. So, he can better his payoff by bidding more than player 1's bidding, which is B1, and get the object, make a positive payoff. So, the player 2 will have a profitable deviation in this case. If B1 is greater than V1, is that a Nash equilibrium? Again the answer is no, because here player 1 is getting the object, but he is making a negative payoff. So, that is not good for him. So, he can at least bid to B1 is equal to V1, and that will give him 0 payoff. So, again, so from here also there is profitable deviation for player 1. So, we have basically shown that if these conditions of A are not satisfied, then we do not get Nash equilibrium, which means that Nash equilibrium implies A. The other part is this. It is written in the question itself, that any profile satisfying A is Nash equilibrium. So, we have to show that A implies Nash equilibrium, and this is not very difficult to show. So, any profile satisfying these characteristics is a Nash equilibrium. This is true because look at the possible deviation of any player. In this case, player 1 is getting the object. Either he is getting a 0 payoff or he is getting a positive payoff. If he is getting a 0 payoff, which means that B1 is equal to V1. From this, if he bids more, then he is going to get the object, but his payoff is going to turn into negative. So, that is not good for him because right now he is getting 0 payoff, from 0 to negative is bad. If he bids less, then he is not going to get the object, which means that his payoff remains 0. So, deviation for player 1 is not profitable. This is the case where B1 is equal to V1. If B1 is less than V1, the player 1 is making positive payoff. If he raises his bid, he is still getting the object, but his payoff is going to go down because the payoff is given by V1 minus B1. If he reduces the bid, he is going to lose the object. So, payoff becomes 0, which is worse than a positive payoff. So, deviation by player 1 is not profitable. For the other players, any player, it may be 2 or 3, any player, if they want to change the outcome by bidding more than player 1, they are going to get the object, but as we have seen before, the payoff is going to turn to negative. Right now they are getting 0 payoff, so that is not good. If they bid something less, then they are still not getting the object. So, outcome does not change, and so payoff remains 0, hence deviation by other players is not profitable. So, this any profile which is satisfying this set of characteristics is going to be a Nash equilibrium. So, therefore, we have proved this, that A implies any. So, unlike, what is the moral of the story? Moral of the story is that unlike second price auction, first price auction has the equilibrium in first price auction has some definite characteristics, and these characteristics basically bound the equilibria into some limits. They are not as wide as in the case of second price auction. They cannot be anything, they have to satisfy some characteristics. Now, in second price auction, we saw that there are some other characteristics, for example, Vi weakly dominates other actions of I. So, this was second price. Now, one may wonder if this property hold for first price auction also. So, is it the case in first price auction, does Vi weakly dominate other actions? And it turns out that some of the actions are weakly dominated by Vi. So, suppose this is Vi and I am considering Bi which is greater than Vi. Then one can see that Vi weakly dominates any action which is greater than Vi. This is because it depends where B bar is. If B bar is here, then bidding Vi gives you 0 payoff, bidding Bi gives you negative payoff. So, Ui is equal to 0 if Vi is bid and is equal to negative of So, in this case if B bar is less than Vi, then it is better, Vi is a better action than Bi. If B bar lies here, then by bidding Bi you are getting the object, but your payoff remains at this value which is negative, whereas by bidding Bi you are not getting the object. So, your payoff is 0. If B bar is here greater than Bi, then both the bids, that Vi and Bi, gives you give you 0 payoff because you are not getting the object. So, the player is indifferent. So, we see that considering all possible cases, we see that bidding Vi is either better or it gives you the same payoff as bidding Bi. Therefore, Vi weakly dominates Bi. But is that true for any action which is less than Vi? And the answer is no. So, if Bi is less than Vi, in this case what is important to see is that by bidding Vi you will always get 0 payoff in case of first price auction, because what you are, if you get the object, your payoff is Vi minus Bi and Bi is equal to Vi. So, your payoff is 0. If you do not get the object, obviously your payoff is 0. So, by bidding Vi you are always going to get 0, but by bidding Bi can you do better? And the answer is yes. Suppose B bar is here less than Bi, then by bidding Bi you are going to get Vi minus Bi, which is positive. So, there are cases where Bi is better than Vi, and if B bar is here, then by bidding Bi you are not getting the object. So, your payoff is 0, but we have seen already that by bidding Vi also the payoff is always 0, and same logic holds if B bar is greater than Vi. In this case, in both Bi and Vi the payoff is 0. So, in some cases bidding Bi is better than bidding Vi, and in other cases they are same as far as payoff is concerned. So, if Bi is less than Vi, Bi weakly dominates Vi. So, any action which is less than the valuation of the person is a weakly dominating action compared to the valuation of that person. And this implies, if I put these two things together, that any action which is greater than the valuation is weakly dominated. Any action which is equal to the valuation is also weakly dominated. We have seen this here. It means that in Nash equilibrium which satisfies this characteristics, remember this characteristic, which means that in Nash equilibrium action of at least one player is weakly dominated. One is basically talking about this action. I know that there is at least one player who is taking the action B I, and I know that B I is going to be greater than or equal to V 2. Even if it is equal to V 2 and if I is equal to 2, that is player 2 is taking this action, even then we have seen that V 2 for player 2 is a weakly dominated action, which means that in that case also the one action is there in the equilibrium profile which is weakly dominated. And if obviously if B I is greater than V 2, then that is going to be weakly dominated. Now, this is true, but this is true if we consider only in the cases where we have continuous variables. If we do not have continuous variable, if the variables are discrete, which means that there are some units of the variables below which we cannot divide the variables. In that case, however, we can have equilibrium in which nobody's action is weakly dominated. I can give you the example in the following sense, that suppose epsilon is the lowest unit, discrete unit, and in that case what is a Nash equilibrium? What is one example of a Nash equilibrium? I can take the following Nash equilibrium. So, here epsilon is the smallest unit in which these valuations can be divided into. By the way, this is a wrong spelling. And here player 1 is bidding V 2 minus epsilon, player 2 is also bidding V 2 minus epsilon, and other players are bidding B 3, B 4 etc., where B j suppose is less than equal to V j minus epsilon for j greater than 2. So, for other players they are bidding something either equal to V j minus epsilon or less than that. Now, I am claiming that this is a Nash equilibrium. Why this is a Nash equilibrium? Because here player 1 is getting the object, as we already know that must happen in Nash equilibrium. But player 2 is bidding same as player 1. If player 2 bids a little bit more, then he will get the object. If he bids V 2, he will get the object. But if he bids V 2, his payoff remains at V 2 minus V2 which is equal to 0. Right now also he is getting a 0 payoff by not getting the object. So, by deviating, player 2 is not better off. If he deviates to some less value, then obviously he is not getting the object still, and so his payoff remains at 0. Player 1 will obviously not deviate, he is getting a positive payoff. If he bids more, he still gets the object and the payoff goes down. If he bids less, his payoff becomes 0. And other players will, if they change the outcome, then they get negative payoff. If they do not change the outcome, their payoff remains 0. So, this is Nash equilibrium, but look what is interesting in this Nash equilibrium is that everyone is bidding less than his valuation for the object, and if everyone is bidding less than the valuation, then the actions are not weakly dominated, because we have seen that those actions which are equal to or more than the valuations are weakly dominated, not actions which are less than the valuation. So, this is an action, this is a profile where nobody's action is weakly dominated, and if epsilon goes to 0, then this profile approaches V2 it approaches this, and in this equilibrium player 1 still gets the object, pays V2, and remember this equilibrium is similar to other equilibrium in the second price auction. This, in the sense that in that auction, in this profile also, in second price auction, player 1 is getting the object and he is paying a price which is equal to V2. So, as far as the amount of money which is collected from the auction is concerned, these two profiles, this is in first price and this is in second price, are known as revenue equivalent. They, both of them are giving the same revenue to the auctioneer. And another similarity between these two profiles, equilibrium profiles, is that in both these profiles action of no one is weakly dominated. So, these two profiles are called distinguished equilibria. Let us do one exercise which extends our first price and second price into what is known as third price auction. Consider its third price sealed bid auction, which differs from first and second price auctions only in that the winner, that is the person who submits the highest bid, pays the third highest price. There are at least 3 players. Now, the things that we have to answer is the following. One is that show that for any player I, bid Vi weakly dominates any lower bid, but does not weakly dominate any higher bid. Secondly, show that the action profile in which each player bids or valuation is not a Nash equilibrium. And thirdly, find a Nash equilibrium. So, the questions that we have to answer, firstly, Bi less than Vi is weakly dominated by Vi. This we have to prove. So, this is more or less it. This is the end of the lecture for today. Before we wrap up, what are the things that we have discussed? We have looked into the various aspects of the first price sealed bid auction. We have seen that first price sealed bid auction satisfies many interesting properties. In equilibrium, player 1 always gets the object. In equilibrium, 2 bids must be same, one of them is player 1's. And also we have seen that this Nash equilibrium, if we take continuous variables, will have at least one action which is weakly dominated. And if we do not take continuous variables, if we take discrete variables, it is possible to find Nash equilibrium in which the actions are not weakly dominated. Thank you. How many Nash equilibria are there in first price sealed bid auction? Give some examples. So, the answer to the question is that there are infinite number of Nash equilibria in first price sealed bid auction, and we were supposed to give some examples of such Nash equilibria. For example, suppose B1, B2, Bn, these are the bids. So, suppose player 1 is bidding same as his valuation V1, player 2 is bidding the same thing, and the other players are bidding their own valuation. Now, my claim is that this is a Nash equilibrium. The reason is that we have to check whether players can deviate and be better off. Here, one's payoff in equilibrium is given by V1 minus V1, which is equal to 0. So, he is not getting anything, though he is getting the object. Similarly, 2's payoff is not getting the object, and other players, none of them are getting the object. So, their payoff is 0. So, the question is, can someone deviate and earn a positive payoff? The answer is no. For example, player 1 can deviate and bid something more than V1, but remember, if I bid more than V1, I will definitely get the object, but my payoff will turn out to be this, which is negative. So, it is not good in my interest to bid more than V1. If I bid less than V1, in that case I am not getting the object, player 2 will get the object, and if player 2 gets the object, he will get something I do not know, but I am not getting the object, but I am not better off either. So, here this is 0, which was the same thing that I was getting earlier in the equilibrium. So, this is an equilibrium indeed for player 1, at least player 1 cannot deviate and be better off. Similarly, for other players also, if they have to get the object, they have to bid more than V1, and if they bid more than V1, then their payoff becomes negative. So, from none's point of view, this is any profitable deviation is possible. Another example we can give is the following. Take this or let us say
this, just change, make it more interesting, because otherwise the payoff of the first player will be same as the payoff of the first player in the previous equilibrium that we cited. Here what is happening is that player 1 will again get the object, and his payoff will be V1 minus V2, which is positive. So, he is now getting a positive payoff. Can he be better off? Well, he can bid more than V2, but then his payoff falls. If he bids something less than V2, he loses the object, which is strictly bad. So, deviation by player 1 is not profitable. For player 2, if he has to get the object, he has to bid more than V2, which means that his payoff will turn out to be negative, which is worse than getting 0. For the other players also same logic applies. So, this is an equilibrium. Second question, in the equilibrium of the first price sealed bid auction, action of at least one this should be at least one bid is weakly dominated. Explain. Now, interesting property of Nash equilibrium in the first price auction is that the first two bids, highest bids, will be equal and between V1 and V2. So, we have here V1 and here V2. So, the first two highest bids must be somewhere here. Now, we have another property of this first price auction, that bidding more than one's valuation or bidding equal to one's valuation is weakly dominated. So, if we have such equilibrium here, then at least one player who coming from this set, that is player 2, 3, etc., n, at least one of them is bidding more than his or her valuation in this range, and that action we know is weakly dominated. So, therefore, in every equilibrium in first price auction, at least one player's action is weakly dominated. So, that is the meaning of the statement. Thank you.